In this exercise, we'll analyze the RVfpga SoC's I/O system and do some tasks to use and modify it. We've seen the RVfpga system before, but now we'll focus on how peripherals connect via the wishbone bus. This diagram shows the EH1 processor connected through an AXI bus, which is orange here, to a bridge that converts AXI bus signals to a wishbone bus, shown in gray. Here we can see the peripherals connected via a 7-to-1 multiplexer to the wishbone bus. As we can see, an address decoder uses the most significant bits from the core's address to select one of these 7 peripherals, while the least significant bits are used to address registers in the I/O controllers. In this slide, we can see the memory map of the SoC used by RVfpga. In this lower section, we see the address ranges for each of the 7 controllers shown in the previous slide, and at the top, we see the space reserved for RAM. The SoC doesn't include a memory controller, but it reserves this initial address range for users to connect to RAM via a memory controller. In this table, we also see the same info, the address ranges occupied by each controller's registers, and finally, this table shows the registers used to communicate with the 7-segment displays we'll use in this lab. Specifically, there are 2 registers, enables and digits, located at these addresses. Let's start by analyzing the simplest peripheral in the SoC, switches and LEDs connected through a GPIO controller. GPIO stands for General Purpose Input-Output. This first slide illustrates a generic simplified GPIO. The GPIO module allows the processor to read or write a pin connected to a simple peripheral like a switch or LED. Pins can be configured as input or output, offering flexibility to connect to various devices. This figure shows a simple GPIO consisting of just one pin. It connects to a device like an LED or switch via a tri-state buffer, allowing GPIO configuration for input or output mode. The GPIO has 3 1-bit registers in this simplified case. The read register containing the pin's value reflects the state of a connected switch. For instance, 1 if it's on and 0 if it's off. The CPU can read this register via a memory address to determine the switch's state. There's also a write register, which holds the data to be written to the device. For an LED, the write register determines if it's on or off. A 1 means on and a 0 means off. Again, the CPU can write to this register, controlling the LED's state. Lastly, the enable register configures the pin as input or output. Its value, 1 or 0, sets the pin to input or output mode. Moving on to the specific implementation we use in RVfpga for this peripheral. The GPIO we use was obtained from the OpenCores organization via this link. It's an open source GPIO written in Verilog and consists of 32 pins, numbered from 0 to 31, with each one being similar to the generic GPIO we explained in the previous slide. Like the previous one, it has read, write, and enable registers. In this case, each of them has 32 bits, associated one-to-one with the device's 32 pins. The addresses where these registers are mapped are shown in this table: 8000-1400 for read, 04 for write, and 08 for enable. This slide shows how the GPIO connects to the RVfpga socket. We can see the SoC, which we saw in previous slides. The core, the 7-to-1 multiplexer, connects each peripheral to the core. Here we have all peripherals, including the GPIO that links to the board's switches and LEDs. The board has 16 LEDs and 16 switches, so a 32-pin GPIO is ideal for connecting these components. Here's an expanded view of the connections. The enlarged GPIO controller shows how the 16 least significant pins connect to the 16 LEDs. For instance, pin 0 connects to LED 0, pin 1 to LED 1, and so on. The 16 most significant pins link to the switches. We see pin 31 connecting to the leftmost most significant switch, pin 30 to the next, and all others follow the same pattern. In this presentation, we'll show how to configure, read and write shock switches and LEDs. At the top, we see how the GPIO is configured. In our shock, the least significant pins are connected to LEDs, which are output devices, and the most significant pins to switches, which are input devices. We'll set the 16 right pins as output, 1, and the left as input, 0. First, we store the enable register address in T0, the value to write in T1, and use store to write that value to the address. This program will set the GPIO enable register to 16 zeros followed by 16 ones. In the middle, we see how to write to the LEDs. Let's say we want to turn on LEDs 15, 3, and 0. First, we read the address of the write register for the LEDs, which is 1404 in the GPIO we're using. We write this address to T0, and in T3 we store the value we want to display. We want to turn on LEDs 15, 3, and 0, so the value is 8009 in hexadecimal. We then store this value at the address. This writes 8009 hex to register 1404, which in binary is a 1, followed by zeros and ending with 1001, turning on the intended pins. Lastly, we see how to read switches in the 16 least significant bits of register T. We write the read register's address, 1400, to T0, read it into T5, then shift T5 right by 16 positions. Why? Since the switches are connected to the most significant pins, 31 to 16, what's read will be in those positions. To place them in the least significant bits, we'll need to shift 16 positions to the right. If the switches were like this, the read register would show 110000 based on which switches are up or down. This is the value read in T5, and after shifting 16 bits right, T5 will contain this value. Note that the GPIO we're using has more registers than the 3 we've discussed. It includes registers for interrupts, GPIO auxiliary input multiplexing, and others we'll use later. Let's look at an RVfpga BitBow app that reads switch states and copies them to LEDs, turning on LEDs for on switches and off for off switches. The code's in the Alternative Projects folder, LED switches. We'll open it in VS Code for students to analyze. Now we'll run it on BitBow. We'll start the Python server, which is already running, and the BitBow simulator. In the browser, connecting to the board shows the switch states reflected in the LEDs. Let's analyze the 7-segment displays on the board we're using. We'll start with a high-level overview, then dive deeper and modify the driver. Seven-segment displays have, as the name suggests, 7 segments that can be on or off. This device can show decimal digits and some letters. To display a 1, we turn on segments B and C, leaving others off. For a 3, we light up A, B, C, D, and G, while keeping F and E off. Our Nexus A7 board has 8 7-segment digits numbered 0 to 7 from right to left. As we mentioned, the Shock has a controller to communicate with this device. It includes 2 registers. The enables reg at address 80001038 and the digits reg at 80001013. The first register, enables, controls whether each digit is on or off. Specifically, the rightmost bit, E0, controls whether digit 0 is on or off. Note that this register is low active, meaning a 0 in the corresponding bit turns the digit on, while a 1 turns it off. For example, if E7 is 1, digit 7 turns off. If E7 is 0, that digit turns on. The digits reg contains the 4-bit encoded information to be displayed on each of the 8 digits. The controller lets us display all hexadecimal digits from 0 to F. So if we have 0000 encoded in a digit, what we're showing in that corresponding digit is a hexadecimal 0. If we have 0001, we'll show 1, and if we have 1111, we'll display F. This slide shows an example where we'll write 71 in the two rightmost digits of the 7-segment display. For this, the enables register must have the hex value FC, as this sets the two rightmost bits to 0, turning on the two rightmost digits, while the next 6 bits are 1, which turns off the other 6 digits. The digits register, on the other hand, should contain the 71 we want to display. A possible C implementation of this functionality would be what we have here. In the main function, we write to this address the seg_add address defined here for enables, we write FC, and to the digits address associated with the segdig_add macro, and is 103C, we write 71. Then we stay in an infinite loop to see what's displayed on the screens. Alright, now let's see the code we just explained in action. We'll use the RVfpga to bitbow simulator, though it would work the same on the actual board. The code, exactly as it is, should function identically on the board. Let's open the virtual machine and access the bitbow project. Projects RVfpga to bitbow. In the C file, we'll replace the existing code. We'll use the code from the slide instead. Remember, it writes two registers to display 71 on the right two digits. We need to save it. To run bitbow, first launch the simulator in VS Code's bitbow extension, compile, and let it run. Then, in the terminal, go to Verilator SimBitbow folder and start the Python server. There it is. Finally, in the browser, we open localhost 8000/nexus7.html. On connecting, the program displays 71 on the right two digits and turns off the rest. Note, in the simulator, digits appear outside the board. On the actual board, they're in this position. Now let's segment 7 displays at a low level. This figure shows 8 digits on the left, each a 7-segment display. On the right we see 1 digit in detail. As shown, the digit connects to a common anode with individual cathodes. The anode signal determines if the digit is active or inactive. If inactive, the digit will be completely off. If active, each cathode determines whether its segment is on or off. Looking at the left figure, we see 8 digits receiving 2 8-bit signals each. The AND signal spans bits 0 to 7, with CA to CG signals each 1 bit, plus an unused P bit. Each AND signal bit, from and 0 to and 7, corresponds to the anode of a specific digit. For instance, and 0 is digit 0's common anode, while and 1 is digit 1 ES, distinct from and 0. This allows us to control each digit's activation or deactivation independently. The cathode control signals, however, are shared across all digits. CA, for example, is identical for every digit. CB controlling this segment here is also the same for all digits. So how can we display 8 different digits if cathode signals are shared? We'll explore this next. In this slide, we explain how we display an 8-digit number on the 8-digit 7-segment displays using the controller for 7-segment displays in the RVfpga SoC. As shown in the figure, it outputs two 8-bit signals needed for the device to function, and 0 to AND7 and CA to CG. This circuit illuminates each digit individually and in order, starting from the rightmost digit and ending with the leftmost, repeating this process indefinitely. When a digit is lit for a brief moment, the cathodes display the pattern for the desired value in that digit. As we move to the next digit, cathodes change to show the new numbers pattern, repeating this process. The human eye can't perceive a digit turning off before it lights up again, so all 8 digits appear to be constantly lit, showing the desired 8-digit number. For more info on 7-segment displays, check the board's manual by searching Nexy's A7 reference manual online. Look for segments there. You'll find a whole section describing this device. The controller takes two inputs, enable_reg and a_digits_reg, linked to memory mapped registers that set the 8-digit value to display. It outputs the AN and CA to CG signals, as seen earlier, which the 7-segment display needs to function. Remember, the activation signals are active low. This slide demonstrates how the 7-segment display controller operates. Let's say we want to display 71 with the first 6 digits off and the right 2 showing 7 and 1. The controller will function as follows. During the initial time period, bit 0 of the AND signal will be low, while all other AND signal bits, 1 through 7, will be high, activating only the rightmost digit. For segment control, only B and C signals will be low, which turns on those segments. B and C segments form the EOL 1E, so lighting these while others are off displays a 1 in this digit. In the second period, we'll move to the second digit. Bit 1 of the AND signal will be low, while all other bits will be high. We'll set segments A, B, and C to low, which are these ones here. As a result, the second digit will display a 7. Periods 3 to 8 won't light up any digits, so the AND signal will be completely high, meaning no numbers will be shown for digits 3 through 8. This process repeats, resulting in the leftmost digits being off, the first 6 turned off, and the 2 rightmost digits continuously showing 7 and 1. This final slide shows the complete RVfpga system, detailing the 7-segment controller. This is the RVfpga system. The core, AXI bus, AXI to wishbone bridge, and wishbone bus connecting to device controllers. The core, shown here enlarged, generates AXI bus signals. Four of these signals affect the 7-segment controller's operation. The controller receives wishbone bus signals that write the desired number to the enables reg and digits reg registers. These registers are connected to the 7-segment display controller, which functions as explained earlier to generate AND0 to AND7 and CA to CG signals controlling the number displayed on the 8 7-segment display digits. Next, we'll examine the Verilog implementation of the 7-segment display controller. The code is in the master's SRC folder, including shock, swerve off shock, peripherals, and system controller code. We'll analyze this code, focusing on the 7-segment display controller part. In the next slides, we'll explain the code regions relevant to 7-segment displays. Let's start with memory-mapped registers. Recall that the controller has 2 memory-mapped registers, enables reg and digits reg, each with a unique address. The controller receives signals from the core via the wishbone bus. This code section shows how data from the core is assigned to the registers, allowing us to control what's displayed on the 7-segment displays. Note that the register address is chosen based on comparing this number with the address's least significant bits. Next, we see the instantiation of the 7-segment display controller, which is named as such, self-seg displays controller. This module implements the controller, and these are its input and output signals. As we can see, the controller receives enables reg and digits reg as inputs, along with clock and reset signals. We saw this in the diagram, these 2 registers as controller inputs and outputs for 7-segment display operation. Here, digits bits refers to individual bits CA to CG, which are controller outputs for the 8 7-segment displays. Now let's analyze the implementation of the 7-segment display controller. To achieve the operation described earlier, where 8 digits light up one by one showing their values iteratively, we'll use a counter with a high number, outputting the count value. It starts at all zeros, then all zeros and a 1, and so on until all ones. The counter will then reset to 0 and start again. We'll use the most significant bits, which change slowest, as the control signal for a multiplexer. This will activate each of the 8 digits in the device. This slide shows the code region for the multiplexer that generates the enables. The multiplexer output is the AND signal, which enables the device's digits. Input has 8 options: rightmost digit active, then second, third, fourth, fifth, sixth, seventh, and eighth. The control signal uses the most significant bits of the count, as explained earlier. On the other hand, this is the multiplexer implementation that generates the digit signals. The output is deck number. Note that this isn't directly passed to the device but needs slight transformation, as we'll explain later. The input is the value each digit from 0 to 7 must take. Notice it's encoded in hexadecimal, with each digit using 4 bits to represent a hex number. The control signal is the same as explained in the previous slide. Now returning to the output signal, deck number, it can't be directly provided to the device because it's in hex and needs decoding to pass the correct bits for each cathode of the digit we're currently displaying. For example, to show a 0, we need to turn on all the segments except G in the middle, and that way what we'll see on the 7-segment display is a 0. To conclude, let's explore how to use the RVfpga system with interrupt-based I/O. Until now, we've used programmed I/O where the program constantly polls input devices for changes, or it won't notice them. Interrupt-based I/O differs. Devices notify the processor of state changes, allowing it to do other work and only react to interrupts. The RVfpga SoC has an interrupt controller with 2 external lines, one from a timer and one from the GPIO. Remember, the GPIO connects to the board's switches and LEDs. We could use register level interrupts, but it's complex. Luckily, Western digital libraries offer functions to configure and use interrupts. In our upcoming programs, we'll utilize these functions. To wrap up, let's look at a simple example using interrupts. Specifically, switch 0 will be managed through interrupts, so that each time there's a transition from 0 to 1 on the switch, it'll send an interrupt to the processor. The provided project, which we'll see shortly, has a main function that basically sets up both the interrupt system and peripherals. It also has a GPIO init function that mainly configures GPIO for switch 0 to work with interrupts. And then there's the GPIO ISR interrupt service routine function, which runs every time an interrupt reaches the processor. This function handles the interrupt task, which toggles the least significant LED when switch 0 goes from 0 to 1. First, it reads the current LED state, then inverts the rightmost LED, and finally writes the new value to the LEDs. Lastly, it clears the interrupt and re-enables it from the switch. Now, let's look at the interrupt-based code example we just described. In the VM, we open the project in Alternative Projects, LED switch, 7-segment display, interrupts, clang. This project has a C function like we just described. If we scroll to the bottom, we'll see the main function, which initializes the interrupt system and peripherals. It has a GPIO initialization function that sets up interrupts for switch 0 and a GPIO ISR function that performs the previously described functionality. We launch the application in RVfpga Bitbox, start the Python server, and run the simulator. On the virtual board, we see a count on the 7-segment displays, which we hadn't mentioned before, but more importantly, each time we toggle switch 0 from 0 to 1, the corresponding LED inverts. The LED toggles when raised, not when lowered. The interrupt only triggers on 0 to 1 transitions. We can do this as quickly as we want, anytime, and it always has the same effect.